So, we have seen that alpha c and alpha d, the attenuation constants, they are function of frequency for any given guiding structure. So, let us see how they varies with frequency. We are considering different dimensions. Let us consider for X band operation first. So, these are the plots of alpha c. We have three different situations with three different dimensions. The first case, B is equal to A. That means the broadside dimension is equal to the height of this waveguide. And in second scenario, what we are doing, we are changing the thickness to half. So, B is equal to A by 2. So, for the first one, we see the plot of alpha c, it is having much smaller value compared to what we have for B is equal to A by 2. So, A is the broadside dimension, B is the thickness of this rectangular waveguide. So, as we change the thickness B, electric field value it increases with the decreasing B, and not only that, the current density on the metal surface it also increases with decreasing B. So, what we expect, then the attenuation constant due to this ohmic loss, it will be more for a reduced height, as we can see it here also. So, for the same B is equal to A guide, the TM11 mode it appears at much higher frequency. So, for both these two cases, at cutoff frequency it goes to infinity, and if we increase frequency they decreases. Now, one of the main advantages of rectangular waveguide is least loss. So, we will not operate the rectangular waveguide near its cutoff frequency, otherwise it will be lossy. So, we have to operate the waveguide at higher frequency compared to FC, but again then we have another limitation. Then if we keep on increasing the frequency, at higher frequency we have higher order modes. The first one, let us say TM11 mode it can appear, then TE20 mode can appear. So, all of these higher order mode excitation they depends on the dimension of the waveguide. And if we calculate lambda g value for each and every case, we have twice pi by beta, it is always more than lambda naught, or in other words phase velocity it will be always higher than c. So, that means rectangular waveguide it supports only first wave, the TE mode it is a first wave mode. Next, the same plot of same alpha c, and also we are plotting alpha d for different scenario. Let us first consider air filled rectangular waveguide, two different dimensions, one for the X band operation and the second one is in terahertz frequency range. We are considering smooth surface, so no surface roughness is there. Then these are the plots of alpha c for these rectangular waveguides. The first one for A equal to 0.5 millimeter and B is equal to 0.25 millimeter, and the second one it is reduced height. So, B is 1/4 of A, as we expected that red line which corresponds to the thinner waveguide, it is giving higher alpha c value. Right side for the X band, this is for the standard WR90, A is 22.86 millimeter and B is equal to half of this. We have cutoff frequency approximately at 6.35 gigahertz, and blue line corresponds to the alpha c variation of W190. Now, if we reduce the height by a factor of 0.5, in that case alpha c increases, but look at the values, it is of the order of 10 to the power minus 4 dB per millimeter, and in left hand side it is 0.05 to 0.1 dB per millimeter. If I operate it in this region above 400 gigahertz, so typical loss value will be 0.03 to 0.04 dB per millimeter. So, if I compare this value with printed lines like microstrip or CPW, it will be at least 20 to 50 times higher than rectangular waveguide. It can be a few dB per millimeter at this 300 gigahertz or 400 gigahertz frequencies. So, that is why at terahertz frequencies we can't use printed line. Now, let us introduce some dielectric inside the waveguiding structure. So, the same waveguide with similar dimension, but we are using a dielectric material of dielectric constant 2.2 and the loss tangent is 0.002. Then the plot of alpha c is this, and alpha d, you see alpha d again it's infinite at cutoff frequency and then it decreases, but it has an optimum point above which it again slowly increases. So, this alpha d it represents the dielectric loss and alpha c it represents the conductor loss. So, total loss it will be then alpha c plus alpha d. So, look at the cutoff frequency values. In the first figure we started at 300 gigahertz and in the second figure we started at 200 gigahertz. Why? Because of this epsilon r. Previously it was air field, epsilon r is 1, and in the second case epsilon r is 2.2. So, cutoff frequency it decreases by a factor of root epsilon r. And right side it is showing the same waveguide but with reduced thickness. Now, B is equal to A by 4. So, alpha d and alpha c they have again similar variation. The only thing is that now alpha c is higher compared to the previous case. Now, if I combine the effect of both conductor loss and the dielectric loss, then the resultant variation if I plot, again it will be infinite at the cutoff frequency, then it will have an optimum value approximately at 1.5 times of the cutoff frequency, then it will slowly increase with frequency. So, we can say, we can conclude from these plots that for a given rectangular waveguide, dielectric field rectangular waveguide, attenuation will be minimum approximately at 1.5 times of the cutoff frequency. For example, if this waveguide has a cutoff frequency of 200 gigahertz, then we will expect it will give minimum attenuation at 300 gigahertz. How to choose the bandwidth of operation for a given rectangular waveguide? So, we are considering here only alpha c, that means the air field rectangular waveguide. We are plotting alpha c versus f by f c. Now, let us consider a rectangular waveguide cross sectional view. So, broadside dimension is A and its height is given as B. If I consider TE10 mode excitation, then if I plot the field strength, it is maximum on the central plane and the direction of electric field, it is perpendicular to direction of propagation as well as to broadside. So, on the side walls electric fields are 0. On the broad side at the mid plane we have highest current density and JC, and inside the waveguide we have the displacement current component JD, which is maximum on the central plane. So, if I calculate the loss, or if we want to inspect from which place the conductor loss is coming. So, it will be mainly from this middle part, where JC and JD has highest value, and on side walls the contribution of loss from the side walls, it is approximately 0. So, if I consider the effect of surface roughness, then we have to consider surface roughness should be as small as possible on the central plane. Sorry. Now, for TE10 mode, the cutoff frequency is determined by the broadside dimension A. What will be the next higher order mode? It is TE20 mode. If the FC for TE10 mode, let us say 6.5 gigahertz for the given dimension, we know that the cutoff frequency for TE20 mode, it will be just double of this. So, 13 gigahertz. So, considering the effect of broadside dimension, we can use this rectangular waveguide in monomode operation, that means only for TE10 mode excitation from 6.5 to 13 gigahertz. Now, what about the perpendicular dimension? If we keep on increasing frequency, then we may have also TE like mode in this direction. So, let us call this mode TE01 mode, since it is in perpendicular direction. So, for TE01 mode, then the cutoff frequency will be determined by B, and if I want to utilize this whole bandwidth starting from 6.5 to 13, then this B, it should be what? It should be, its maximum value can be A by 2, otherwise the cutoff frequency of TE01 will be smaller than 13 gigahertz. So, that is why for standard rectangular waveguide, we always have B is equal to A by 2. Now, if I go back to alpha C plot for air filled waveguide, we can't utilize this whole bandwidth. Why? Because alpha C, it is infinite at 6.5 gigahertz if it is the cutoff frequency. So, let us go back to the plot then. You see, if the cutoff frequency, this is the normalized frequency. So, f by fc is equal to 1, it represents the cutoff condition. At cutoff frequency or near cutoff frequency, attenuation is high. So, we define the effective bandwidth for monomode operation, where we are expecting only TE10 mode. It starts from 1.25 times of fc to 1.9 times of fc. We have a 10% margin here to make sure there is no TE20 mode excitation, either in A direction or in B direction. And if we have now dielectric material inside, for dielectric material, again the plot is very similar to this. Only thing is that at 1.5 times of fc, it will be minimum. After that, it will slowly increase, and we define the bandwidth again by this number, numerical values, 1.25 fc to 1.9 fc. So, look at this plot. Oh, sorry. So, standard waveguide, its dimension is determined by these cutoff frequencies. For example, for WR90, you can calculate then what is the cutoff frequency, and accordingly you calculate what is the 1.25 fc value and 1.9 fc value. You will see that cutoff frequency for standard WR90, it is coming approximately 6.35 gigahertz, and then the bandwidth it's 8 gigahertz to approximately 12 gigahertz. Now, let us say we are using this rectangular waveguide to design a resonator, we call it cavity resonator. So, it is a closed resonator, we have metal in all 6 sides. Since it provides very low loss, the unloaded quality factor, which is also a measure of loss, it has highest value among all the different resonators from different guiding structure. Typical unloaded quality factor is more than 5000. Now, how to improve the unloaded quality factor further, or how to minimize the loss further for a given cavity resonator? What we can do? So, then we have to minimize the sources of losses. So, for example, if I use a reduced height, in that case we know that loss will be higher. So, we have to use that standard height, at least b equal to a by 2, right. We have to use polished surface, so that the effect of surface roughness is minimum. So, that is how we can minimize the conductor loss. And if we do not use any dielectric inside, then we do not have any dielectric loss. Remember, if air its loss tangent value is approximately 0. So, air is almost considered as a free space or lossless dielectric, but if there is water vapor present in air, it becomes lossy, because water vapor absorbs electromagnetic wave. So, inside whatever material you are using, if it is air, it should be dry, or sometime we have people use inert gas, and you have to make sure there is no water vapor present inside the cavity, otherwise it will become lossy. So, next there is one more method to increase the unloaded quality factor or minimize loss. What is that method? We have very good some very good dielectric available, for which loss tangent is very small. Let us use one such dielectric block inside the rectangular waveguide. Then what is the advantage? Most of the electric field inside the cavity, it will be confined inside the dielectric, and the surface current excitation, it will be minimum. So, this is a technique how we can decrease conductor loss further. Not only that, due to the dielectric, the dimension of this rectangular cavity, it becomes smaller compared to the original one. The actual value of a resonating cavity, the dimension, you can calculate by using an electromagnetic solver or full wave simulator. It is interesting to note that higher order modes, they offer lower loss. So, that means if the same cavity, if I excite it in TE20 mode, it will provide lower loss compared to TE101 mode. Some typical fabrication example. So, nowadays people started using rectangular waveguide for chip to chip communication. So, that means as interconnects, but rectangular waveguide has a problem that it is really very big structure. Its width should be at least lambda g by 2. How we can then decrease the width? We have to use some higher dielectric constant material inside, which has higher epsilon r. Then we can reduce the dimension by a factor of root epsilon r. Even then, we can't use it as interconnect inside a chip because of its dimension, but above 200 gigahertz and typically at submillimeter wave frequency range and at terahertz frequencies, people already started using rectangular waveguide as interconnects. The main advantage is its lowest loss, and why it's above 200 gigahertz? Because of its dimension. Below 200 gigahertz, it's so heavy, so big that we can't use it as interconnect inside chip. So, here are some example of such waveguide structure, and right side figure you can see. So, sometimes also people using air filled waveguide for terahertz application. So, these are some electron microscope photograph taken after fabrication for different types of waveguide structure. So, the middle one is rectangular waveguide, and we also have different shape of waveguiding structure, and they are modeled by this structure given in the left hand side figures. We can determine the characteristics, its propagation constant, its cutoff frequency, alpha beta value by using any electromagnetic solver or even theoretically. Sorry. So, next one is circular waveguide. We are not discussing in details. For circular waveguide, the fundamental mode is TE11 mode, and the next mode is TM01 mode. If you look at the electric field plots which are shown here over the cross section of a circular waveguide. So, for the fundamental mode, it is not symmetric with respect to its axis. The first axis symmetric mode, or it is TM01 mode. So, for different types of application, people use different types of modes. If we need axis symmetric modes, then we have to use TM01 mode. If we want to use just for propagation purpose, then people use the fundamental mode, that is the TE11 mode. Sorry. Rectangular waveguide has one more advantage, that power handling capability is highest. So, before going to discuss about that power handling capability of rectangular waveguide, let us see what are the factors that determine power handling capability of any given guiding structures. It can be rectangular waveguide, air field, dielectric field, it can be any printed lines designed on some substrate, it can be a dielectric channel, anything. So, in general, then we have four factors, those determines the power handling capability of any given guiding structure. So, what are they? The first one is multipaction breakdown. So, this term multipaction might be new to you, I will discuss in details. Then the ionization breakdown, or sometimes we simply call it air breakdown. So, this is the sparking effect, whatever you have seen in day to day applications. Then we have passive intermodulation interference. So, what is passive intermodulation? So, by intermodulation we understand mixing of two signals. So, as we observe for mixers. So, to translate the frequency, we need some sort of non-linearity, and that non-linearity we can, for non-linearity we can use diode, we can use transistor, but for a passive device like rectangular waveguide or for a printed circuit board guiding structure, what is the source of this intermodulation? The source is different types of metals. So, if there is any impurities, it may be very small, its work function is completely is different than the hosting guiding structure like copper. So, they form some non-linearities. So, it can be a metal-metal junction or metal dielectric junction, and it provides some non-linearity, but the effect is very small. But sometimes this small effect also we can't neglect. For example, you consider a mobile base station application or a satellite transponder application, where transmitting power is of the order of watt or of the order of kilowatt, and the received power, it is nanowatt, or sometimes for satellite application it can be as small as picowatt, just below noise floor. So, in that case, for your receiver circuit, receiver is tuned to IF frequency, and for IF frequency it is much small, right. So, for the mixer it will generate your IF, which is the difference between the local oscillator frequency and the incoming RF signal. Now, somehow let us say from your transmitting signal we have the intermodulation product, and a frequency component is being generated due to this intermodulation, which falls in your IF band. So, since its component is very small, this is due to the passive intermodulation. For normal application we will simply neglect it, but for this type of application, when transmitter and receiver they sits together, even a slight leakage, that will be enough to destroy your receiver, because it's falling in the IF band, and the power leakage from your transmitting side, it is small compared to the transmitted power, but not that small compared to the received power, it can be more than that. So, it can completely damage your receiving circuit. So, next one is thermal related high power breakdown and detuning. If we change temperature, then we have seen that dielectric constant, it is a function of frequency, and its epsilon r will change with frequency. So, the operating frequency of the component, it will also change. Now, usually what happens, if we again bring back the original temperature, the dielectric constant, it also comes back to original value, but there is a limiting temperature above which the dielectric, it completely changes its property. We call it the glass breakdown temperature or transition temperature, and also we may face breakdown effect, that is the dielectric breakdown. So, it simply burn the dielectric. Now, let us take a short break, then we will discuss about these different effects in details.